All right, so let's continue with our discussion. And next, we're going to talk about compiling the input-output behavior of neural networks. And in particular, we're going to talk about a really restricted class. This is a very recent development, and that's what we call binary neural networks. But let's just talk a little bit here, because I did realize earlier that some people, they're not familiar with neural networks. So the story is pretty simple. What a neural network is effectively, you can think of it as being made of layers. Here are the inputs, and here are the outputs. It's really like a circuit, like what we've seen, except that what happens at these, if you're going to think of these as gates, what happens inside them is a little bit more involved than just doing a Boolean operation. Inputs, outputs, people talk about these as the hidden layers. These are called neurons instead of gates like we had in the Boolean case. And really what happens is simply you pass an input, and then each one of these guys start computing its output based on the inputs. And that just goes on, and suddenly you have an output. So it's really feed-forward, straightforward evaluation. The two things you need to know about is that each one of these connections has a weight attached to it. So when this guy is computing its output, it's not just the inputs it's getting, but the weights on each one of these guys. So really what it looks like is the following. I'm now blowing up one of these bubbles here, or these circuits, which we call Neuron, and it looks like this. These are the different inputs. So this guy, Neuron, has 5 inputs, and there is a weight attached to each input. And what really happens here to produce the output is something very simple. We take each input and multiply it by the weight, and then add those guys up. So I'm just taking a weighted sum of the inputs. And then now you have a number. You pass it through a function called an activation function, and you got the output. Straightforward. Okay, and I'm going to show you examples of activation functions because that's relevant for our discussion. So it's just a circuit, feed forward, and it's pretty simple. Now, you're going to say, wow, that's basically it? Yes. Now, this gets coupled with 2 concepts that makes it powerful. One of them is I don't specify these weights. I learn them from data. So usually you have what we call labeled data, which is a set of examples where each example is input, output, input, output. And then from those input-output pairs, you can go ahead and learn these weights using gradient descent. This is more like function fitting that you've studied in calculus, except on steroids. So instead of learning the parameters of a linear function or a quadratic function to fit some data, you may have x, y, and I give you points there, and then I'll tell you, go find me a quadratic equation or cubical equation that fit that same story, except that these guys can have millions and billions of parameters. The other major insight is, how do you make up the structure of this guy? And there were some major breakthroughs in that regard, is that depending on the kind of problem, people have found architectures for these neural networks that do very well on certain problems. So you may have heard of convolutional neural network. It's just a particular way of structuring this particular network, which ended up having a huge influence in vision. In our case that we looked at before, where you're looking at a black and white image and trying to tell whether it's a 0 or 1, the pixels will end up being the inputs, and the output is your classification. So there are different kind of neural network architecture. CNNs is one of them. There is also the recurrent neural network people use for language and so on. Okay, now the notion of an activation function, which is this function that after you did the weighted sum, it will go ahead and filter that number again before it produces an output. You hear a lot about initially sigmoid. This is taking a number and effectively generating something between 0 and 1. And here's the formula for it. Okay, so it's just simply weighted sum, pass through a sigmoid, and then generate an output. Or commonly, recently, people use something called ReLU, used a lot these days. And what this guy does is simply take the input. If it's below 0, it suppresses it. It makes it a 0. Otherwise, it passes it as is. Okay. Now, the networks we're going to look at are not going to use any of these. We're going to use something simpler, which is also famous. At least it was one of the more discussed things in textbook on this initially, and you'll see why, because we want to work with something even simpler, and that is what's known as the step activation function. The step activation function is very simple. It basically takes this weighted input, and there is a threshold T. If that weighted input is greater than or equal to the threshold, it passes a 1. Otherwise, it passes a 0. So if you had a step activation function here, then what this neuron is doing is computing the following. X is our input vector. Okay, so here we used I, here we use the variables X. X is your input vector, and I'm gonna go ahead and wanna decide what is the output of the neuron. I'm gonna go look at every value of a variable in this guy. I'm gonna multiply that by the input on X with the weight, sum them, and check against the threshold. All right, so this is basically the step activation function. And I don't know if you're already seeing a similarity between this and something we looked at, but let's make a few observations here. One is, if the inputs to the neuron are in 0, 1, so if these guys are all 0, 1, and I have a step activation function, what does that mean? That means this neuron is doing nothing but implementing a Boolean function. Because you have to realize, for the step activation function, the output is always either 0 or 1, right? Here's your inputs, and here's your, let's say, threshold T here. If the weighted sum is greater than or equal, you're getting a 1. Otherwise, you're getting a 0. So this is here a 1. So what's happening here is this is guaranteed to always generate a 0, 1. But if the inputs are also 0, 1, then that whole thing is just a Boolean function. And furthermore, if I give you now a neural network and I tell you every neuron is using a step activation function, and moreover, the inputs to the neural network are 0, 1, well, the whole neural network is doing nothing but implementing a Boolean function. Now, let's see why. First, why would you have 0, 1 inputs? Here's an example, black and white images. Every pixel is on or off. That's what's going on here. Now, everything is 0, 1 as input. Let's look at this guy. All of its inputs are 0, 1, and it has a step activation function, so it generates a 0, 1. So this guy is just taking 0, 1s, mapping them to 0, 1. It's doing this through that equation, but it's effectively implementing a Boolean function. You keep going with this, guaranteed the output will be 0, 1 as well. So that actually leads to a relatively simple compilation algorithm conceptually. And now you're starting to see how we end up finishing the story pretty quickly. And the reason we're able to do this is because the reasoning process that underlies neural networks is very straightforward. It's just forward propagation. There's really nothing sophisticated going on like in Bayesian networks, where going from the instance to the class or classification involves a complex probabilistic reasoning process. Now, if indeed we have step activation functions and every input to the neural network is 0 or 1, then that's just equivalent to a Boolean circuit, straightforward. It's a numeric way of implementing a Boolean circuit, but it's just a Boolean circuit. And let's just dig a little bit deeper into this, because now we're going to find some interesting connection to what we talked about. Let's dig a little bit deeper into a neuron with a step activation function and what's going on with it. If I want to show it concretely away from all of this fancy notation, that's what it looks like. That's a neuron that has 3 inputs, A, B, C. This is the threshold T, and these are the weights, right? So this is the weight for the input A, the weight for the input B, and the weight for the input C, okay? And that's what it's doing. It's taking these weights, multiplying by the inputs, adding them up, and then checking against the threshold. And the output is 0, 1. This is known as a linear classifier. So you would say that the step activation function, or the neuron with a step activation function, is nothing but a linear classifier. Every neuron is doing its own classification locally. Have we seen this formula before? Have we seen something like this before, earlier with naive Bayes network? Exactly. We the way we score instances in naive Bayes when we work in log odd space and then check against the threshold is just exactly this form. So what we did there also was linear classification. That is, if you look at the formula behind the naive Bayes classifier, it is a linear classifier. And to see the relevance of this in just a little bit. The piece that's missing here is, how do I get rid of these numbers? As we just said, if the variables A, B, C are Boolean, then this whole thing is specifying a Boolean function. In fact, you can go and plug in different values of A, B, C. There's 8 of them. Evaluate this, check against the threshold, and see the output. So this numeric thing is just doing this. It's a same story we've seen with naive Bayes. And actually, this Boolean function corresponds to the following Boolean expression. So in general, if you give me this guy and say, I'm interested in using this guy to go from A, B, C to a classification, you don't need this guy. If you have this guy, you're good. We'll do exactly the same thing. So what does this mean? This means if I have a way to go from this to that, I'm almost done as far as compiling the input-output behavior of the neural network into a tractable circuit. I'm done as far as abstracting away from the numbers, but I may have to do more to get you a tractable circuit. Let's see it. This is a neural network. Every input is binary. Every neuron is a step activation function. And as we discussed, that means what every neuron is doing is just doing linear classification, which can be replaced by a Boolean formula. So you can think of each one of these guys as taking its input, evaluating a Boolean formula, and generating the output, or evaluating a little circuit, Boolean circuit. So each one of these guys can be actually represented by a Boolean circuit that is equivalent to that linear classifier. So if you want to visualize it, I'm taking the neural networks, but I'm removing every neuron and plugging in a little Boolean circuit. And I'm pasting them together. And now I have a Boolean circuit that is equivalent to the neural network that I started with. That's not tractable. That's just an abstraction. So I got to read from the numbers. Now, if you want to get a tractable circuit, now you have to work more. For example, you can use bottom-up compilation to convert it to something else. And the one thing that is left to be said here is a revisit of the idea of taking a guy like this and producing a Boolean formula. We showed it indirectly using naive Bayes classifiers, because naive Bayes classifiers were just doing this. But it turns out you can now explain it a lot more abstractly. I'm going to show you this in the next slide, which is, how do I compile a linear classifier like this into a Boolean formula or a circuit? We will illustrate the similar concept to what we've seen earlier in this context. And then we will make one observation and we'll be ready. Because now you're telling me, fine, I have this, but how do I get this guy? You know, and I'm going to show you this illustration of how do I compile this guy into a Boolean expression, actually in particular into an OBDD. And again, you'll see something very familiar. It is an abstraction of the algorithm we've seen earlier, but then what's interesting is a complexity result that I'm going to show you later. So you take this guy and say, give me a Boolean expression that is equivalent to this linear classifier. I'm going to show you how to do it actually while getting even an OBDD. We know this trick. This is one of the most important tricks we use throughout case analysis and some kind of depth first search. So you go and say, well, let me pick A. What happens if A is 0? What happens if A is 1? Now, what happens if A is 0? You fix the value of A to 0. What do you get? A subclassifier over only two features, B and C. And this is what it looks. I just filled in 0 for that. You take this guy, A equals 1. You put a 1 here, you get a 2. You move to the other side. Now you get this subclassifier over B, C. And you keep going. And the same story, you can hit some equivalent subclassifiers. And what you'll end up getting is basically an OBDD. So we're doing the same exact thing. We are doing a search in the space of variable instantiations, and we're trying to look for equivalent subclassifiers and make sure we do not do them repeatedly. It turns out this algorithm, which I just showed you, comes from learning theory that was independent of the algorithm that I showed you earlier for naive Bayes. And because it's done this abstractly, it does end up having a complexity result that adds to the complexity result that was known about the naive Bayes classifier. I'm going to share this with you in just a little bit. But again, what's missing here is the caching scheme. But in this case, the caching scheme ends up being somewhat easier to explain. So this algorithm also comes with its own caching scheme for recognizing when sub-classifiers are equivalent. We're not going over this, but that should be a simpler story. The highlight of this is the following. In a sense, this is a more abstract formulation of a problem that we've seen earlier with naive Bayes. The original naive Bayes compilation algorithm came with this guarantee, which basically says the worst case for compilation is exponential not in the number of features, but in half of those. Now, we know we can easily be exponential in the number of features. That's when you build a decision tree, right? And the worst case here was no, you don't. I can guarantee you, you will not be more than exponential in half. So that's significant. So if you had, let's say, 50 features, being exponential in 50, no, you can't do it. Being exponential in 25, you can. But that's worst case. That algorithm actually, the average case complexity is way better than this, but still an interesting bound. And the theorem from learning theory actually says more. It says if your parameters are integers, what are the parameters? Remember, these guys. For the naive Bayes case, those are not integers. Those were actually real numbers. But the result from learning theory says if these guys are integer, then I can guarantee you complexity, which is this. N is the number of features. What's W? W is the sum of the weights. So if you take these weights, it's sum of the absolute values. So you've got the threshold T and you've got the weights. You take the positive or the absolute value of these guys, add them up, that's this big W, and then you're linear in that. This is interesting because this is a complexity result that is specific to the numbers or the weights that you have. So now you have a worst case complexity and another complexity. This is not dependent on the numbers, but this is dependent on the numbers. And you can use this guy even where your numbers are not integers when they're real by fixing the precision. Right, exactly. In fact, Ellie just mentioned that. Indeed, Ellie. And then you won't get exact computation, but you will get, in fact, if you see the paper, we'll post it. You'll be surprised that sometimes you work with not a lot of precision, and that doesn't change things. So yes, you can use fixed precision, convert them to integers, and still use this algorithm. And it actually gets used as an approximation algorithm compared to the original one that I showed you. But let's not lose sight of the big picture here. Neural network, each neuron is doing something like this, taking a weighted sum and passing through a step activation function. And that's nothing but actually a Boolean circuit. And as long as you know how to compile each one of the neurons, its own little subcircuit, you have abstracted behavior. And this was used for these examples that I mentioned last time. They were using this technique actually. And, you know, they learned the neural network on a particular data set, and you've seen the examples that it produced, which is pretty cool, that you can reason about the behavior of the systems symbolically and do things like explanations and robustness. All right, folks. So that's pretty much what we wanted to say about neural networks. This is a relatively simple class. And of course, people do more things with more general types of neural networks. There's quite a bit of literature there. It doesn't necessarily compile into tractable circuits, but it does compile into some other kind of symbolic representations. And then different kind of boxes and techniques gets used, including SAT solvers. So in the remaining time, I would like to talk about decision trees and random forests. And there's two parts to the story. The part about how do I take a decision tree or random forest and abstract its behavior symbolically, that actually is straightforward, and you'll see why. Because these creatures are already in symbolic form. Where it gets a little bit interesting, and this is a situation that's not specific to random forest and decision trees, but it's more apparent here, is this notion of going from Boolean variables to discrete variables. Now, we kept mentioning every once in a while, variables do not have to be Boolean, they have to be discrete, or they can be discrete, like in Bayesian network. Now, here we have to really get to it because you'll see why. You need to address this to do anything interesting with these creatures. And then there is a subtlety there, which is important to talk about. This is a very recent observation, and it's actually surprising given what's known there. So there's two dimensions. Let's get going with this. So the discussion about Boolean versus discrete requires us to start working with discrete variables. And at the pure logical level, that's actually a straightforward story, and I hope to convince you with that here. We've seen this example before about earthquake, burglary, alarm, where each one of them was true or false. And when we did that table, we had only 8 worlds, right, corresponding to all combinations. And in this case, we can assume that alarm is a discrete variable. It could be high, low, or off. Now, if you look at the set of worlds, it's a very similar story, except that I have more combinations, right? Now I have 12 worlds instead of 8. And you can define what you may want to call multi-valued propositional logic. Now, what does that mean? That means in Boolean logic, my variables or my primitives were either a variable or its negation. And here I'm going to do something a little bit more general. I'm going to allow you to say that the alarm is off. This is what I'm going to view as my primitive. And then I can write sentences like earthquake and B equals true implies alarm equals high. Look what happened here. Multivalued, so I have to say A equals something. We did 2 things here for E and B are both binary. Here I will use the old standard thing. If I put the variable E, I mean E is true. Here I made it more explicit by saying B is true. So for Boolean variables, you have 2 choices. You can specify B equals true, or you can just say B, same thing. And E, here I'm saying equals true. So you could say B equals true, or just B, or you can go ahead and say B equals false, or just not be the same. Everything from there on stays the same. You can define the syntax. The only thing we added is this thing, is you're allowed to say this. And I hope you can imagine that if I come and tell you, here's the world, does this satisfy this formula? That's straightforward. You just go to the literals and plug in their values, true or false, and then you evaluate this guy. That doesn't change anything. Whether world satisfies the sentence, whether a sentence is consistent, whether 2 sentences are equivalent, everything follows, okay? So that's what we mean by multi-valued propositional logic. And when we say multi-valued expressions, we're gonna mention things like that, all right? Now, no, the values do not have any orderings in our case. So we are just going straight for discrete values. Now, let me mention another concept before we go into decision trees and random forest. And this is the notion of discretizing a continuous variable, because you're going to see in random forests and decision trees, typically people work with continuous variables. And then you may be thinking, oh, wow, how are we going to handle this using logic? Well, here's the thing. So in this case, I have 2 variables, continuous variables, X and Y. And both of them can take values from negative infinity to infinity. But suppose I tell you, look, all I care about is whether the variable X has a value in this interval or this interval or that interval. Otherwise, I don't care. Well, even though X is a continuous variable in this case, you can go and represent it using a discrete variable that has only 3 values, X1, X2, and X3. With the understanding that X1 means that the continuous variable has values here, X2 means it has values there, and so on. So the point is, if you have continuous variables and you only care about their values belonging to certain intervals, you are now in the world of multi-valued propositional logic. And that's what happens with decision trees and random forests. So let's look at an example decision tree. What happens here is the variables X and Y are continuous. But look what's going on. The decision tree is saying, okay, I'm trying to classify an instance which is defined by a continuous variable x and a continuous variable y. I'm trying to classify it into 0, 1. It doesn't have to be 0, 1. You can have discrete labels. And here's how I'm going to do it. I'm going to start by asking, what is the value of x? If it's greater than or equal to 2, go this way. What is the value of x again? If it is greater than or equal to 6, the label is 0. Otherwise, okay, let's go this way. What's the value of x? It's less than 2, go that way. What's the value of y? If it's greater than or equal to -7, go this way, label is 1. Okay, there are indeed continuous variables here, but I don't need continuous variables. I can basically do the discretization that I mentioned and say, let's just talk about discrete variable x having 3 values and discrete variable y having 2 values. And then when you have a test like this, what does it mean x greater than or equal to 2? That means it's either in this interval or in that interval. So that test here is effectively x1, sorry, this is x2 or x3, Boolean expression, right? Is it in this interval or that interval? You see what's going on? So the interesting thing is, where did I get this discretization from? That's the machine learning algorithm that is learning the decision tree. Usually you give it labeled data similar to neural networks, and it comes and learns this. And in the process of learning, it decides how to discretize the variable x into checking whether it's greater than 2 or 6, dot, dot, dot. The point is the discretization happens by the learning algorithm. So you don't have to worry about that. The learning algorithm has done all of your work. It did actually do the abstraction for you. And now you're ready to move on. Now, once you see this, then, okay, how do I capture the behavior of a decision tree symbolically? Well, now it's straightforward because, look, I mean, now that we did this, the whole decision tree can be viewed as a discrete function, right? What I have is 2 variables, x, y. Each one of them could have a certain number of discrete state. You look at the combinations, you draw your combinations, and this guy is just taking each instance of these and labeling it with a 0, 1. So even though this whole thing has continuous variables, it's nothing but a simple discrete function in this case. Think of these as your worlds, right? In this case, x has 3 values and y has 2, so you have 6 combinations. And it turns out I can give you a Boolean formula, not just, this is a table. This table is going to be exponential, but you can get a Boolean formula relatively easily that captures this Boolean function. And the idea is simply to think of each path as a conjunction, right? There's a test, Boolean test, and a test, dot, dot, dot. So each path can be easily written as a Boolean expression that correspond to that path materializing. And if you know how to do those, we'll just show you. You can just take the ones for the one labels and disjoin them. So, for example, if we go down here, we just agreed that this means that it's x2 or x3, right? Because I'm here. Now, if I'm here and I go down there, what does that mean? X greater than or equal to 6, that is being in this interval. That's x3. But if I go down here, that's not x3. So da and da. And under this condition, this tree will label the instance as positive. If you do the same for this guy, and you take their disjunction, you got yourself a Boolean formula or a multivariate expression for this particular decision tree. Okay, it's pretty straightforward. And in random forest, and this would be the simple case, is you usually have a bunch of these trees, and then before you do a classification, you ask each one of them what it thinks, and then you combine these classifications. For the case of majority voting, that would be straightforward, to combine the Boolean formulas into one big Boolean formula that actually is checking whether a majority of them said yes. So now you can see it's pretty easy to take decision tree and map it into a multivariate expression that captures the same logic. That's straightforward. That's well known. For random forest, depending on how you're doing the combination, majority voting is straightforward. One subtlety that I want to mention and I will end up with, and this is recent, is the following. What do you do with this guy? Now you have a multivariate expression, not a traditional Boolean expression. And if you want to do analysis, let's say you want to do PI explanations or sufficient reasons. And how do you do that? How do you compute these guys? Let's just focus on that. There are two trends when you have this situation. One of them says, well, first of all, define what is a prime implicant in this particular case. I'll show you. It's straightforward. And then develop an algorithm dedicated to computing prime implicants of multivariate expression. You can't go down that path. However, because people have developed so much machinery for Boolean logic, there's also a tendency and say, I want to build a new algorithm for this thing. I already have a box that can compute prime implicants for Boolean expression. Can I do a reduction? Can I take this multivariate expression and represent it as a Boolean expression and you capitalize on the algorithms that I have for prime implicants on the Boolean level? It turns out to be yes, but you have to be very careful. And I want to tell you about that now because that's actually very recent and surprising. People have been doing reductions all along. They've been mostly doing reductions for satisfiability. That is, if you want to check the satisfiability of a Boolean expression or a multivariate expression, I reduce it to a Boolean one and I use the traditional SAT solver. And now we're trying to do something different, compute prime implicants. There is a complication there. But first, let's settle what does it mean to be a prime implicant in this setting. Again, this is important. Discrete variables are pretty important and they end up being abstractions of continuous variables. So that's practically very important. And we'll post a paper on this if you want to get into more details. It's almost a tutorial-like paper. So now we're talking about multivariate variables. So every variable has a bunch of values. The notions that we talked about in the Boolean level start generalizing. You have to be careful though. What is a literal? A literal in the Boolean setting is just a variable or its negation. Here, a literal is an expression. You can say whatever you want as long as you only talk about one variable. So you expect this to be a literal, but we're going to define this also as a literal because what this is just a constraint on the value of a single variable b. So think of a literal as a constraint on the value of a single variable. This is a literal. This saying that c cannot be high, which effectively means it's either low or medium. A term, as we do it usually, is just a conjunction of literals. Okay, here's one term, here's another term. And then you can define subsumption in the usual way. This is the definition of subsumption in Boolean logic. You can do it the same thing here. And you can define the notion of an implicant in the same way, prime implicant. Everything carries over from our discussion on Boolean logic. The only generalization here was, what do we mean by a literal? What do we mean by a term? And in this connection, you end up finding a need to make a distinction between what we call a simple term. A simple term where every literal really fixes the value of a variable. So in this case, A is true, B is R, C is high. That's a simple term. This guy is not a simple term. Why? Because it does not fix the values of every variable. It says A is true, but it says B could have a whole bunch of values. C could have a whole bunch of value. So this guy specifies two possible values for this guy, two possible values for this guy. So in a way, this more general term is actually representing four possible simple terms. Okay. This is taking our notions from Boolean logic and mapping them to the multivariate setting. Now we're going to end up with this subtlety or recent observation, which is pretty important. I want to do manipulations on this guy, like computing prime implicants. Why do I want to do this? Because we've seen the role of prime implicants in generating explanations. So what I want to do is, instead of developing a dedicated algorithm for this, I want to take it and write it into a Boolean formula and use a prime implicant enumerator on this Boolean formula, and then from that get the sufficient resistance. Can I do that? The idea is I want to capitalize this box. I have boxes that people have built for doing prime implicant generation, and I want to capitalize on them. And realize in this story now we're bypassing tractable circuits altogether because we're assuming you're just gonna get a Boolean expression of the behavior and then operate on it directly. The main thing I want to mention is the following. There are reductions from multivariate expressions to Boolean formulas, and they've been around for a while. And there is one particular one which is pretty famous from maybe a few decades ago. And you may end up discovering it on your own if you were to do this. And people usually used it for things like satisfiability. I want to do satisfiability on this, but instead of building a SAT solver for multivariate expressions, I reduce it to Boolean formulas and use a classical Boolean formula. And those reductions, they will not work if you want to do what we're trying to do here. That is, you cannot use those reductions as is to compute prime implicants on the Boolean and then map those to prime implicants on that guy. I just want to give you a sense of it. The solution ends up being relatively simple, but if you really want to understand why, you have to dig deep a little bit into things and be comfortable with certain Boolean manipulations. We'll post it. This is in the same paper about reducing decision trees into Boolean expressions. So let's see it. The idea is whenever you do a reduction, you need to think about what are you trying to preserve. If you're trying to preserve satisfiability, that's one thing. If you're trying to preserve model counts, that's something. If you're trying to do prime implicants, that's yet another thing which has not been explored before until recently. So the particular reduction, or people call it encoding, that is encoding a multi-valued expression as a Boolean expression, that one is known as the one-hot encoding. And it's the intuitive one. It's the one that you would expect, which basically says, you know, I have a multi-valued variable X, it has these values. I'm going to introduce one Boolean variable for each one of these values, okay? In fact, let's just do that. Let's just say I'm going to have Boolean variables x1 through xn. And the idea is if this is true, that means this variable has that particular value. If this is true, that means this variable has that particular value. And in this case, something like this, you can represent it as, okay, you can do this. And you can just like add these. So this is one way of doing it, that it wasn't this, it wasn't this, it's this, it wasn't that. And you would add, and in principle, you can also just do this here, and then you add what people call exactly one constraints. Now, I want to say that, no, this variable, if it takes x1, it cannot take another value, and it must take one of these guys. So you end up writing something like this, x1 or x2 dot dot or xn. That means the variable must take a value. And then you add a bunch of these that says, oh, it cannot take two values if it cannot be x1 and x2 at the same time. So these guys ensure that precisely one of these Boolean variables will be true. And you take these exactly one constraints, you add them to the Boolean formula that you get by substituting each one of these guys to something like this, and then you got your Boolean expression. The problem is that alone, and then you may say, you know what, let me now go compute prime implicants on the Boolean formula that I just showed you, the reduction plus the exactly ones constraint, and then I transfer these back to prime implicants on the multivariate expression. Doesn't work. So show you a simple example here. And then again, the solution ends up being simple, but Y is more complex. This is my multivariate expression. It's pretty simple. I have two variables, X and Y, each has three values. So x1, x2, x3, y1, y2, y3. So, okay, this is the multivariate expression. According to what I showed you, the way you would reduce this to a Boolean expression is just like this. You take this guy, replace it by this, take this guy, replace it by that. Okay, you add or you OR, and that's Boolean now. And then these are your exactly one constraints. So now the idea is I'm going to work with this instead of that. Now, look at this guy. Intuitively, is x1 equals this value? Is this term, is it a prime implicant of this? Intuitively, prime implicant is something that satisfies the formula in a minimal way, right? So in this case, if I tell you that x has this particular value, then I'm satisfying this formula. You can't make it any simpler in this case. So that is a prime implicant. Now, here is this guy with all its models. And here is this guy together with that with all its models. And if you look here, you will see that while x equals x1 is a prime implicant of this formula, this term, which is the encoding of this guy, is not a prime implicant of this Boolean formula. You want to think of this as or, because these are models, right? It's not. So it doesn't work. And that was interesting because one-hot encoding, people will say, well, just do one-hot encoding and you're done. No, you're not done. It depends what do you want to do. And if you do the classical things that people do, like do satisfiability, you're done. If you want to do something more involved, you got to be a bit careful to make sure that this still works. And to give you just a very short story on the solution, it will spark your curiosity if you want to read more about this. The idea is you do not want to compute prime implicants of this, but instead you want to compute the prime implicant of something else. Okay, we're not going to go over this. I'm just showing you an example of the kind of things you have to get into if you want to understand the details of the story. But the idea is, don't compute prime implicants of this guy. Compute prime implicants of this instead. And then when you do that, you have to filter the result a little bit more. So keep only those terms that are consistent with this. Okay, now I know this is mysterious, but that's part of the point, maybe to get you to see why do you get in trouble if you compute prime implicants of this and why you need to do it that way and filter. But the story is the picture end up looking like this. You take a multi-valued expression, you do a one-hot encoding, you get this guy, and these are your exactly one constraints. So now you take this expression and generate prime implicants of it. You still have to filter some of them and you get your prime implicants or sufficient reasons. Okay. And the final outcome is simple, but why do you have to do this instead of the other more intuitive is a little bit of a more involved story for those who are into logical reasoning at a deeper level than what we're covering here. There would be an interesting story to follow. Folks, we're pretty much done here. I want to end with something that I believe, ended it with last time, about this big picture of reasoning about the behavior of machine learning systems, where we are reasoning about what was learned, and to make 2 points. It's a fascinating story. The bottleneck with it is this. Now, for Bayesian networks and random forest, it is this. The bottleneck is this, because we know how to abstract. But the question is, will our abstraction algorithms scale, right? If you give me enough time and space, I can always, using the current algorithm that I have, to map a Bayesian network classifier into a Boolean representation or into a symbolic representation. I can do this also for decision trees. It's just a matter of scalability. Neural networks is a different story, because neural networks, we just showed how you can do it for simple things, simple kind of activations and under assumptions of input being 0, 1. It's not just a challenge of scalability. It's a challenge of abstraction when you have different kind of neurons. So this is one thing. The other thing that I wanted to stress, which is I mentioned before, and I hope now you appreciate it a little bit more, conceptually, the easiest is the random forest. And I hope you can see that, because they're already abstracted. They're already effectively symbolic. The next is neural network, in the sense that I'm abstracting a forward reasoning process. There is really nothing subtle about how reasoning works. The one that is more intricate is Bayesian networks, because for Bayesian networks, in between the instance and the decision on it or the classification sits a complex reasoning process that is not evident from the structure of the Bayesian network. And you're trying to actually kind of get through that to do the compilation. So that's basically what I'd like to say today. And we will be, maybe in this case, putting a little bit more optional reading than usual for this, because that actually covers quite a bit of stuff that's been happening over the last couple of years. And you may follow up on some of that. Thank you, guys. This is all for today. And I will see you on Thursday.